Okay, this is my last video on stationary waves, and it's all to do with waves on a string. So you need to know is well to give examples of stationary waves, example waves in a string. I'm not going to cover here open pipe microwaves. You need to know what's meant by the fundamental frequency. Draw diagrams the first, second overtone, linking wavelength and frequency. And finally, this is all to do with guitars, linking the pitch of a note on the string to its frequency, also to the tension of the string, or tension in the string rather, and the mass per unit length of the string. So if I was in a lab, I would have this set up for you. I'll basically have a nice long piece of string here, make it vibrate up and down, and show you these wave patterns, but unfortunately I don't. So we'll have to do it by a simulation. So this is vibrating up and down, and what it's doing is sending out a wave going along here. It hits the end over here, the clamp stand, and then it reflects back. We now know we've got superposition, and then we get a stationary wave. Now, that's doing it at 5 hertz, and it all looks very boring. If I suddenly increase the frequency up to 15 hertz, suddenly you can see what I call the one eye. Now, you can see the string vibrating and a stationary wave is formed. We have the node in the center, and you've got, antinode in the center, and your node here and here. Now, I've slowed it down so you can see it forming. In reality, that's what you can see. If I now increase the frequency to 30 hertz, you can suddenly see what I call the two eyes. Now here you've got a node there and a node there, and now you can see two antinodes. And you might have guessed it, if I now go up to 45 hertz, you see three eyes. And again, you've got your nodes, antinodes going through here, which happened 3 times the first frequency. And now we go up, just about squeeze it in, 60 hertz, you can see the 4 eyes. Okay, now why is this happening? Well, to show you why it's happening, what's going on is I can go through this. Now going back to here, this one is called the fundamental. It's the lowest frequency to get a stationary wave formed. Now to analyze it, we can call this is going to be the length of the wave, which I'm going to call L. Now here's going to be your node, and here's going to be a node, and the center we've got an antinode. We think about it here, haven't I got half a wavelength? Therefore, I can say the length of the wave is going to be lambda over 2. Rearranging the equation, I now have lambda is equal to 2L. Well, I know from equation that C equals the frequency multiplied by the wavelength. Well, in that case then, isn't the frequency going to be C over lambda? Therefore, if I got F equals C over lambda, I can take this equation here and bung it in for the wavelength. Therefore, won't the frequency equals C over 2L? Now, it's important to realise this C now is the speed of the wave travelling along here, well, the progressive wave and reflecting back to form the standing wave. We call that the fundamental frequency because the lowest frequency we get a standing wave. Then, if I go to this one, is now this happens at 30 hertz. Or why is it 30 hertz? Well, again, you've got your nose going across like this. Here's then going to be your length of the wave. Now can you see the fact the length of the wave is a full wavelength? Going back to my equation, C equals frequency multiplied by wavelength. Therefore, the frequency is now going to be C over lambda. Bunging that in, isn't that then going to be F equals C over L? Because I know lambda equals the length of the wave. Now hang on, didn't I know, first of all, the fundamental frequency from this one, F equals C over 2L. We call this the first overtone. Can you see that one to this one? All I've done is multiplied that by 2 to get hold of this one over here. Therefore, hence, wouldn't it be twice the fundamental frequency? 15 times 2 makes 30. This one again makes sense. Here, what I've got now is I've got the second overtone. Now, can you see here again is going to be your length of the wave. Now the length of the wave, isn't it going to be 3 lambda over 2? Because I've got 1.5 wavelengths. rearranging the equation, won't now the wavelength equal 2L over 3? Hang on, C equals F lambda. Therefore, the frequency is equal to C over lambda. So if I bung that in here now, here's going to be C, and now then the wavelength is going to be 2L over 3. Okay, well, in that case then, and I'll tie this up a little bit, we call this then the second overtone, so I'm going to call it F2. Rearrange the equation looks a bit neater. The 3 will pop out. Isn't that going to be now 3C over 2L? Well, the fundamental F0 was going to be basically C over 2L. How do I get from here to here? I multiply by 3. Therefore, doesn't it make sense? Your overtone, the second overtone, equals 3 times your fundamental frequency. And you can go all the way up then to the 60 hertz and find it's 40. So the 60 hertz can be 4 times the fundamental. Now that explains how we get his waveforms here, but also anybody, a budding guitarist, you can make this fundamental frequency change. And this will do it tuning a guitar. And you should know by changing the tension of the string, you change the pitch or the frequency, but also you change the length, which is basically going to be the length of the string here by putting your finger at different points in the frets, don't you? Well, this all comes in this equation here. In this equation here, this is all to do about the fundamental frequency, and it's in your formula sheet. That should really be F0, but I think the formula sheet says F. And the equation pops out, it's 1 over 2L, which is going to be your length of the string here, okay, which is the length where you put your finger on the frets, but you've got this one and this one here. Now, the first one makes sense. T stands for tension. In other words, if you change the tension of the string, you're then going to change the fundamental frequency. And you can see that F is proportional to root T. But also then is this mu here. Now the mu is the mass per unit length. Now, if you ever played a guitar or had a go at a guitar, these strings here going along, these are quite heavy strings and these are light strings. Therefore, the light strings make a higher pitch note or a high frequency, and the heavier strings make a low pitch note. That's because the fundamental frequency is going to be proportional to 1 over mu or root mu. Therefore, if you start making the string heavier, heavier, and heavier, and heavier, don't you bring down the pitch? That equation you need to know. Now, I'm also going to, probably in this post, bung on an exam question for you to have a go, and that'll leave that for you to play yourself, and you have got the answers to it as well. Anyway, hope you have a good understanding about waves and string. Bye for now.